As we continue using our trigonometric ratios, we are going to use them in solving for side lengths of right triangles. And we want to be able to write equations using our trig ratios that can be used to solve unknown side lengths of right triangles, and then solve for unknown side lengths of right triangles using these ratios and apply those in real world problems. Okay, so just remember, sine is equal to the opposite over the hypotenuse. That is my cosine is equal to the adjacent over the hypotenuse. And then my tangent is going to be, not tangent, my TOA is going to be the tangent is equal to the opposite over the adjacent. And that comes from, again, sine, opposite, hypotenuse, cosine, adjacent, hypotenuse, tangent, opposite, adjacent. So there you go. Those are, we want to remember those as we're going forward with our using our ratios. So we have here this example, and what can I figure out with this example? Let me see. I can figure out that I've got a right triangle. My triangle is going to be ABC. I have my opposite sides measured out here, and then I have this angle. And then I hope everybody knows that what this angle is over here. Well, if C is 90, B is 50, that means the remaining angle is going to be 40 degrees. And when I look at angle A, or if I look at angle B, so if I go with the sine of 50 degrees, that is going to be the opposite, which is going to be B over the hypotenuse, which is going to be C. There you go. The cosine of that 50 degrees is going to be the adjacent, which is A, over the hypotenuse, which we said was C. And then the tangent of 50 degrees is going to be the opposite, which we said was B, over the adjacent, which we said was A. So there we go. We're able to figure out those ratios, and I mean, we can turn around and do the same thing for angle A. So the sine of 40 degrees is going to be the opposite, which we said was A, over the hypotenuse, which is C. The cosine of 40 degrees is going to be, let's see here, the cosine is going to be the adjacent over the hypotenuse. And then finally, the tangent is 40 degrees is going to be the opposite, which we said was A, over the adjacent, which we said was B. And there you go. What do you see? Any relationships there? It looks like the sine of one acute angle is equal to the cosine of the other acute angle, right? So that is a relationship that we can identify. And in doing so, we might notice that the sine of 40 degrees is going to be equal to the cosine of 90 minus some angle, and we said that that some angle is 50, or 40 degrees, which is the sine of 40 degrees is going to be equal to the cosine of 50 degrees, which is going to be its complementary angle, okay? So looking here, and again, that's just tying a little bit of a relationship together. So what is the value of x? Well, in this example, in order to find this, they've given me an angle. So I have this angle, and then I'm trying to find x, and what can I find with x? Well, x is going to be the opposite length. So if I'm dealing with the opposite length and they've given me the hypotenuse, the opposite and the hypotenuse, well, that tells me then the useful trigonometric ratio for me will be to use the sine function. So if I have the sine of 50 degrees, that is going to be the opposite over the hypotenuse. So the sine of 50 degrees is going to be x over the hypotenuse, which is 6. Now, in order to isolate x, well, I need to do my inverse operation. So I'm going to multiply both sides by 6 to get that 6 out of the denominator. And I'm going to have 6 times the sine of 50 degrees is equal to x. So what I can do is I can plug this into the calculator. And when you put this into the calculator, you want to make sure that you are using the mode that you are in is in degree mode, because you are going to have two possible modes. So, and as you can see here, I'll take a quick picture. Okay, so what I've done here is first this little picture right here. If you go to mode, and you want to make sure that you are in degree mode, and radian mode is something you'll use in different types of math and functions. But for now, we want to be in degree mode because we are working with degrees. Now, when we go to plug this in the calculator, right, I got 6 times, simple enough. Remember, we multiplied both sides by 6. So I have 6 times the sine of 50 degrees equals x. So you just plug that into the calculator. So I have 6 sine, and when you first put that in, the first parentheses will appear, and then I typed in 50 for degree. So again, here is the sine. So I hit 6 times sine, and then typed in my 50, and then in parentheses, and hit enter, and I came up with this value. So it looks like x is going to be equal to, I'm just going to go ahead and round that to the 10th, 4.6 centimeters. And there you go. Now, if we wanted to turn around and find y, we could do the same thing. Now, to find y, I'm going to want to, let's see here, y, if I'm looking at 50 degrees, that is going to be the adjacent. So in doing so, the cosine would be the adjacent over the hypotenuse. So cosine is the adjacent over the hypotenuse. So the cosine of 50 degrees is going to be equal to y over 6 centimeters. So again, we multiply both sides by 6. So I have 6 cosine of 50 is equal to, and that is going to be equal to 3.85, or we'll just say 3.9. So y is equal to 3.9. And there you have it. We just, depending on what they gave us, depended on what ratio we wanted to use. And let's see here, moving on to our next example. A right triangle has one side that measures 4 inches, and the angle opposite that side measures 80 degrees. What is the length of the hypotenuse of the triangle? All right, so I have this triangle, and we know that this is going to be 90, and then it tells me that I do have an angle that is going to be 80 degrees. So we have a right triangle right there, has one side that measures 4 inches, the angle opposite that side. So this is 4 inches because that is the angle opposite, or the side opposite 80 degrees. What is the length of the hypotenuse? Ooh, goodness. Okay, so the hypotenuse right here, and they've given me the opposite, so it looks like I would want to use my sine. sine of 80 degrees is equal to the opposite, which is 4 over the hypotenuse, which is x. We'll call it x because we don't know it. So then do some inverse operations, right? Multiply both sides by x. So I have x sine of 80 is equal to 4. And then isolate further by doing dividing both sides by sine of 80. So the sine of 80 cancels that out. So I have x is going to be equal to 4 over the sine of 80 degrees, which is going to be, so it's going to be 4.06, or we'll just call it 4.1, is what my hypotenuse is going to equal. So that is barely longer than the other side. So if we were to draw this more to proportion, it might look something like this. And then, of course, this would be 80 degrees. This would be 10 degrees. There you go. And let's see here. So what more do I need to include in these examples? What is the side length of CD? Right here. And it says round to the nearest tenth. Okay. In order to find CD, I currently don't have anything. But I do know that, angle D is equal to 25 degrees, and CD would be adjacent. So CD is adjacent. CD is adjacent. Well, one thing I can do is if I look over here at this triangle, I do have 30 degrees here, so that tells me I know that this is 60. And then I know that there are some ratios out there that I could fill in, but I won't at this point in time. And then I know that this should be 65 degrees. What can I do? I could find out what this is. That is the opposite to my 30 degrees. Because they've given me the opposite or the hypotenuse. So if I say that the sine of 30 degrees is going to be some value, right? Opposite, so we'll just call that maybe x, over the hypotenuse, which is 12. So I'm going to go ahead and do my inverse operations and multiply both sides by 12. So 12 sine of 30 degrees is equal to x. So x is going to be equal to, let's see what the calculator is going to tell me. 12 times the sine of 30 degrees is going to be equal to 6. So x is equal to 6. So this is going to be 6. Well, now I'm getting closer to being able to figure some stuff out, because I could use the Pythagorean theorem here to figure out this missing value, but I don't need that missing value. I'm looking for segment CD, and I know that that is going to be, if I look at D, going with angle D, the opposite, I have the opposite, and then that would be the adjacent. So I'm looking for the tangent. So the tangent of angle D is, or the tangent of 25 degrees is going to be equal to the opposite, which we said is 6, over some value we don't know. We don't know what CD is. So I just gave it a y. Let me see here. Tangent of 25 degrees is equal to 6 over y. I'm going to go ahead and multiply both sides by y. So y times the tangent of 25 degrees is equal to 6. Go ahead and divide both sides by the tangent of 25 degrees. And then y is going to be 6 divided by the tangent of 25 degrees. So 6 divided by the tangent of 25 degrees is equal to 12.9. So it looks like CD right here is 12.9. So segment CD is equal to, it was equal to 12.86, but I did say, the question does say round to the nearest tenth, so it is equal to 12.9. There you have it. Solving for side lengths using my trigonometric ratios. And there you have writing those equations using those ratios. Write equations using the trig ratios that can be used to solve for unknown side lengths in right triangles, and then solve for unknown side lengths of right triangles using those trig functions, and then apply those trig ratios to real world problems. So solving for side lengths of right triangles, and we will continue to work with our SOHCAHTOA, and hopefully the more we work with it, the more proficient you become.